So last lecture I think we stopped while we were discussing delays. So we'll finish with that discussion, finish with the introduction, and then start on discussing the application layer. You might have seen the website has been updated. It's moved to its permanent home. The bulletin board is up. The first homework should be up today sometime. And also I'll be giving you the first programming assignment. It should be up maybe Thursday or by next Tuesday, and it'll be due sometime early October. The due date is not decided. So that programming assignment, right now my thinking is that we'll build on that programming assignment throughout the semester. So initially, the programming assignment would deal with topics that deal with application layer. And then slowly as the semester progresses, we might add functionality to that program in the transport layer and the routing layer. So that's the thinking initially. We'll see how that goes. The other thing is, as I said, you can do your project either in Java or C. And the book does a fairly good job of explaining socket programming in Java. What I'll do in class, instead of going over that again in Java, I'll explain socket programming in C. And C is also sort of, socket programming in Java is very easy, but it hides a lot of details of what's really going on with the network. And when you see those things happening in C, you get a better sense or a better idea of what all is involved in writing a distributed or a network application. So we'll be doing Java socket programming using C in class. So last lecture, where exactly did we stop? We were discussing delays. I'm sorry? Losses, okay. So delays, we had discussed 4 kinds of delays. There was the nodal processing delay. There was the transmission delay. Propagation delay. And finally, the queuing delay. So if you look at, let's say a router. So this is the symbol that's sort of universally used for a router or a switch. And your data is going between 2 routers. So your packets are being transmitted between these 2 routers through a link. Then the delay in transmitting the bits from one router to the other router is the propagation delay, and that depends on the speed of light. So this propagation delay is dependent upon speed of light and the distance. So this is propagation delay. When the packets arrive, so let's say a packet arrives here, and the packet will have information on the header of where the next destination is, and also things like checksums and other error correcting or error checking processing is done at the routers. So that happens before anything else happens at the router. So that's the nodal process delay. So that delay, you can think of that as happening right before the router. The transmission delay happens right here. That's the delay in putting this entire packet which has arrived, which has been processed onto the link. So this is the delay, which is the transmission delay. On putting the packet onto the link. So I'll reiterate or repeat what I had said yesterday or the last lecture, that transmission delay and propagation delay are very different quantities. Transmission delay depends on the bandwidth of the link. So how fat your pipe is, or how much data it can transmit, whereas propagation delay is simply dependent upon the speed of light and the distance involved. So your link could be 10 megabits per second, 100 megabits per second, 1 gigabit per second. But if the distance is not changing, then your propagation delay is going to remain constant. So propagation delay is dependent upon speed of light and distance. Transmission delay depends on how fast can you put the bits onto your link. And that is dependent on a number of different things. So what kind of modulation schemes you are using, how many time slots do you use, how many frequency slots do you use. It depends a lot on physical layer stuff and link layer stuff. Yeah?
Two questions. Does the propagation delay overlap with the transmission delay? If you're in the picture?
No. No, it doesn't. So starting here, let's say this is the link.
And also, why is it dependent on the speed of light?
The propagation delay, because these bits are being transmitted electronically. So they go either on a wire, where again the rate of this transmission of the signal depends on the signal speed of light.
But is it on the speed of light even if you're not using an optical fiber?
Yeah, even if it's going on a metal fiber, it's still being transmitted using some kind of modulation or an electronic signal, and the speed of that signal is the speed of light in that material or in that medium. So it's always dependent upon the speed of light in that material. So yeah, the transmission delay does not overlap with the propagation delay. Now, the fourth kind of delay, which is a queuing delay, that happens when data arrives in bursts. So you're getting a number of packets arrive in a burst here at this router. Now, how could that happen? When your input, when the incoming bandwidth is higher than the outgoing bandwidth, then what that means is this router cannot process all these packets and put them on a link before the next one arrives. So that would involve queuing up of these packets at this router. So imagine a situation where you have a fast Ethernet connected to a wireless access point. The fast Ethernet is capable of transmitting data at 100 megabits per second. But the wireless access point can only send data to the next wireless hop at, let's say, 11 megabits per second. So data can potentially arrive at 100 megabits per second. So this is the rate at which it's arriving. at this access point, and it's being sent to the next access point at a peak rate of 11 megabits per second. So clearly, you cannot sustain the input rate with the output rate. So these packets will get queued at this router. And this queuing is also the major cause of losses on the network. So when this queue grows really large, the figure that I drove last lecture of queuing delay, or the average queuing delay versus load, and it looks something like this. As the load goes to 1, the queuing delay goes to infinity, blows up to infinity. But in reality, in no physical system can you have an infinite queuing delay. What that really means, what this is showing is how many packets you can expect will be waiting at the buffer, at the router. Now this router has to store these packets in a buffer. And any physical router will have a finite size buffer. So when the incoming rate becomes high, your queuing delay does not go up to infinity. The queuing delay is, let's say, limited to the size of the buffer. But any packet which is arriving when the buffer is full will get dropped. So most of the losses on wired networks happen because of queuing. So this is the source of losses. Queues overflow, and that causes packet losses. And when we study TCP, we'll see how, in the transport layer, how TCP tries to adjust its sending rate so that these losses are minimized. But that will come in the details of that will come in the transport layer. It's a very clever algorithm, and one of the main reasons why the internet has scaled and has remained stable is because of the way TCP was designed, so that it could adjust to losses and it could adjust its rate so as to not cause these buffers to overflow. So we'll look at the details of TCP design when we come to the transport layer. So that tells us about the causes of delay and loss on the internet, and these are the major factors affecting the performance of any application on the internet. Delays and loss experienced by any flow on the internet. The other thing is these days wireless networks are becoming more and more prevalent, and on wireless networks sometimes the losses are not caused by queuing, but by wireless channel errors or collisions between packets on a wireless network. So if you think of a wired network, let's say you have a router which has a number of incoming links. So in a very simple scenario, you can think of 3 different desktop machines with their Ethernet jacks going to a switch. Now the switch implements some sort of a buffer. So when these three are simultaneously transmitting, as long as your queue is not going to too high a value, these packets can be stored in the buffer and processed in some order. So this happens because in the wired network, these packets can be transmitted from the machine to the router, isolated from the transmission of other packets. In a wireless network, on the other hand, you can't have this kind of a scenario where packets are going simultaneously. They arrive here and in some buffer they get queued up. In a wireless network, what happens is if this is your access point and these are all transmitting, then there is no common buffer which can hold these transmissions if they are going on simultaneously. If these transmissions happen simultaneously, then these packets are going to get corrupted. These bits will sort of corrupt each other. This access point won't be able to decode any of these three packets. So implementing a buffer in a wireless network becomes very tricky. So in wireless networks, the losses are not due to queues overflowing, but losses are more due to collisions of packets. You cannot simultaneously transmit on a shared medium. Thus, that will cause collisions or corruption of each other's data packets. So in wireless networks, the losses are due to collisions or corruptions. In wired networks, it's due to queuing delays. Now let's take a look at how the internet is structured. If we go to the slides. So the structure of internet is it's a network of networks, and it's to a fair degree hierarchical. There are different tiers of networks or different levels of networks, and they are referred to by this label of being a tier 1 ISP, tier 2 ISP, or a tier 3 ISP. So tier 1 ISPs are the biggest networks. They have national or international coverage, and these networks interconnect with each other privately. So data that flows on one of these tier 1 ISPs is privately exchanged with a tier 1 ISP by some sort of agreement. So they have points where they can exchange data with each other. So this creates the first level connection between tier 1 ISPs. So Sprint or AT&T will have pairing points where data that's flowing from the Sprint network intended for the AT&T network get exchanged. There are also these so-called NAPs, or public network access points, where these tier 1 ISPs can exchange data between each other. So the tier 1 ISPs are the main backbone of the internet, and they exchange data with each other either through a private pairing link or through these network access points. So this creates a first level network of these networks. So you have a tier 1 ISP, and it networks with other tier 1 ISPs. An example of a tier 1 ISP is the Sprint US backbone network. This slide shows what the Sprint backbone looks like, where all the nodes are connected and how those nodes are connected to each other. At the second level, you have tier 2 ISPs or regional ISPs. So these are local ISPs that operate in a particular region, like in the New York region or in California or the Midwest. And these tier 2 ISPs will connect to one or more tier 1 ISP. They are all customers of these tier 1 ISPs. They buy bandwidth, or they connect to multiple tier 1 ISPs. So their connectivity is coming through these tier 1 or the backbone ISPs. And once they get connected to a tier 1 ISP through the higher level connection in the hierarchy, they get connected to all the other tier 2 ISPs. So this is level 2 of the hierarchy, the tier 2 ISPs, and these are really the ISPs which customers connect to. So the tier 2 ISP is a customer of a tier 1 provider, and then finally you have tier 3 ISPs or local ISPs. So this is the last hop or the access network to the end systems. So in our case, Columbia is our tier 3 ISP. Our end systems or our machines are provided internet connectivity by Columbia. Columbia provides us with IP addresses, Columbia provides us with bandwidth. And so Columbia is the tier 3 ISP, and Columbia, on the other hand, buys bandwidth from different providers, and it connects to these tier 2 ISPs. For instance, Columbia connection to the commercial internet is through NicerNet. So NicerNet is the tier 2 ISP servicing Columbia, which is the tier 3 ISP, and all of us are customers of this tier 3 ISP. So in a four layer hierarchy, you get connected to the internet. You have your end system, which is provided internet connectivity by Columbia, which is a tier 3 ISP, which in turn gets its bandwidth largely from NicerNet, which is a tier 2 ISP, and NicerNet then goes and connects to Sprint or AT&T or any of the backbone providers. So when you send a packet or you receive a packet on your machine, this packet is going to travel through many different ISPs, and it's going to travel through many of these different networks which are arranged in this hierarchical manner. So it will go through your local ISP, it will go through a tier 3 ISP, tier 2 ISP, tier 1 ISP. It will cross the core or the backbone of the internet, and then again it will travel down to a tier 2 local ISP and to the end system that you are trying to connect to. And this part we have already done. Have you used this program called traceroute? Or have you heard of traceroute? So traceroute, what traceroute does is it'll send packets, and yeah, we are here. Okay, so traceroute is useful in many different ways. Firstly, it'll capture or tell us what the internet looks like at any particular moment. So it'll give us information on the current delay or loss levels existing on the internet. Traceroute also traces the route that your packet is taking between your machine and the end system that you're trying to contact. We'll look at details of how traceroute is implemented later. It was quite an interesting hack it does something which it was not supposed to do. And we'll see how that is implemented. But what traceroute basically does is it will send you information on all routers along the way to the end system. So here you have an example output of trace route running from one machine at UMass to another machine in France. And what this tells you is it first gives you the delay experienced by the packet to the first router. So the first router, the packet that went to the first router, you send 3 copies of it, and they experience delays of 1 millisecond, 1 millisecond, 2 milliseconds. From there the packet goes to the border router, and the delays sort of don't grow much. UMass is the tier 3 ISP for this machine, Gaia, and then UMass, this packet is sent to VBNS, which was the tier 2 ISP for this particular connection. And you see the delay has grown slightly from orders of 1 millisecond, 2 milliseconds to about 15 or 16 milliseconds, because now it's going across larger distances. So initially this packet was only traveling within campus. So the propagation delays that dominate delays are not that high. Then it covers a larger geographical range, so the delays get larger, and once it crosses the Atlantic Ocean, you see the delays jump from 22 milliseconds to about 104 milliseconds. And that's because, again, the propagation delay is dominating. The transoceanic link, the delay there shows up here. The other thing that it's doing, yeah. These are round trip times. Yeah, these are round trip times. The other thing that this traceroute program does, it will tell you all the routers on the way. So it's giving you the name, and when possible the name, and also the IP address of all the routers on the way from this machine to this machine. So you can run this traceroute program on your CS account to different hosts, and you'll see where all the packet goes through in reaching the final destination. One interesting test that you can try is try the traceroute program between a machine connected to Columbia, send it to any other machine on a .edu network. So let's say send it to machines at NYU or Stanford, MIT, and then try the traceroute on machines on the commercial internet. So try a trace to Google or CNN or ESPN, one of those commercial websites, and you'll notice a difference. You'll notice a difference on the path that a packet takes to the commercial websites and a path that the packet takes to these educational websites. And maybe I can ask that question to you in a homework problem. What's the difference and why is there a difference? So packet loss and packet delays we have done. So now we finally talk a little bit about the layering of the network architecture. So as we've seen in the example so far that networks are complex entities. There are many different players in making distributed application share data possible. So you have end systems, you have hosts, routers, You have different kinds of applications running, you have different kinds of protocols running, you have different physical links like wireless or optical or cable. So the question was, is there any hope of organizing or designing networks in a systematic way? And the design philosophy that has evolved over the years is that networks or protocols have to be layered. And the analogy that's given in the book is similar to what we experience with traveling. So a typical organization of an air travel by a person is also layered. There are a series of different steps. The first step is ticket purchase. Second step is baggage check. Then you go to the gates where you go into the aeroplane. Then there's a runway takeoff. The plane gets airborne, and then the air traffic control routes the plane along to the final destination. So what you're doing is you're doing these different steps, and finally when you arrive at the destination, you do these steps in the reverse order. After the routing, the plane lands, you get out of the plane, you get your baggage, and if there's a problem, you complain. The thing to note here is that all of these different steps are sort of isolated from each other. All of these steps provide some service to the steps before or after that, but you can make internal changes without affecting anything else. So your ticket purchase, whether you go to a travel agent or whether you go and buy on the web, does not have any effect or any significant effect on the baggage check-in process. And it has even less effect on the way planes are routed. So by isolating responsibilities and services offered between different steps, you can optimize each step independent of the other. So if you change something in the ticket purchase process, if you try to make it better, that will not affect the takeoff process. So the idea of layering the protocols is to isolate the responsibilities and services that are offered by different layers so as to not affect the functioning of the other layer. So a layer will have some responsibilities, some services. As long as it provides that to the other layer, your system can work, and you can focus in your study or your design on smaller pieces of the entire system. You don't have to look at the whole picture and try to optimize or design the entire system in one go. You break it up into small pieces, break it up into small chunks, isolate the responsibilities, and then design or analyze those smaller chunks. Now there are also so the layering model has sort of been standard in designing of any kind of networks, and especially of the internet. By modularizing different components, you can ease designing, maintaining, or updating of the system. Whenever you change any implementation of a layer service, it's transparent to the other layers. But there is also a school of thought which says that layering might be harmful. There might be cross-layer information that can improve performance. So in the internet architecture, The internet protocol stack looks like this. You have on the top there's the application layer, then you have the transport layer, network layer, link layer, and physical layer. Each layer provides a link to the layers right next to each other. So the transport layer knows about the application that it's serving, and it also knows about the network that it's running on. But the transport layer has really no idea of the link layer or the physical layer. So when is this layering kind of harmful? Yeah.
Using as an example a wireless application, if your transport layer had the information that was going to be moving on a wireless link, you might talk to the application and tell it, let's use TCP instead of UDP to be more reliable and prevent more losses, things like that.
So that's a good example. So if you're, I'll make that example some even more sort of striking. So you're talking about wireless applications. So if an application is running on a wireless network, then the application really does not know what's happening at the physical layer, whether the application is running on a wired network or a wireless network. All that the application can do is run TCP or UDP or any other sort of transport protocol. Now earlier I had said that one of the main reasons that the internet has scaled is because of the way TCP has scaled. TCP, apart from providing reliable data transfer, also provides congestion control in the transport layer. So what TCP really does is, if we go back to the figure where your queue size grows like this, or your queuing delay grows like this, what TCP does, and we'll see how it does that, it'll start sensing when we are reaching this portion of the queuing delay curve. TCP will sense that, and when TCP senses that, then it'll reduce its rate so that the load on the link or on the router becomes lower and it comes to an acceptable level, and your queuing delay doesn't grow that much. So how does TCP do that? TCP does that by looking at losses. Again, what I said earlier was that each router will have a finite buffer, so your queue cannot grow beyond a certain size. If your load becomes higher than this, then the queue doesn't grow, but all these packets will start getting dropped. So TCP senses these packet drops, and then it senses that there is a congestion on the network, and then TCP will scale back. So the assumption here is that these losses are happening because of congestion on the link, because of buffer overflows. On the other hand, if your application is running on a wireless network, then these losses happen because of collisions. They do not happen because of this buffer overflow kind of situation. Now because TCP, which is running in the transport layer, has really no idea what's running in the physical layer, whether it's a wireless transmission or a wired transmission, TCP cannot distinguish between buffer overflow kind of losses and these corruption kind of losses, where packets get corrupted. The TCP reacts in the same manner for both situations, and that causes severe performance problems in wireless networks using TCP, because TCP cannot distinguish between buffer overflows and collision based losses or corruption based losses. TCP reacts the same way, and the reaction on a wired network is the ideal one, the correct one, but on a wireless network it's the wrong one. Now this happens because we've implemented this layering in our protocol architecture. The transport layer does not know what's happening in the physical layer. And if we do inform the transport layer on what's happening in the physical layer, that'll cause some sort of layering violation. So although the layering of the internet protocol stack is by and large very helpful, very good, there are situations where it can be bad. And one example of that is using wireless networks. So if TCP knew that it was running on a wireless network, maybe the congestion control algorithm would be different. It would not rely on this kind of behavior that it expects, but would try and react on what's happening on a wireless link. So all the layering that happens is done through these headers. So when a source is sending some message to a destination, this conversation happens between two different applications. So this application and this application as a source and destination understand what this M message means. At the source, this application will hand over this packet to the transport layer, and the transport layer will add its own header. This header, it gets attached to the message. Then the transport layer hands this segment to the network layer. The network layer will then attach its own header, and this segment becomes a datagram. The network layer finally hands over this datagram to the link layer, which makes the datagram into a frame by adding a link layer header. So you have the original bits, which were the message, and then these headers get tacked on to those bits, and at the link layer you have three different sets of headers. But because of the layering architecture, the link layer does not care and does not know what's happening beyond the link layer header. So when this packet flows and it goes to the first switch will only interpret what's happening at the link layer header, and it gets this packet, it strips off the link layer header, and then it sends this datagram across to the router, to the next router. The router then implements physical layer, link layer, and network layer. The router will then interpret what the network layer header means. It will tell this router where to send this next packet. It'll make its routing decision based on simply the network layer header. The link layer header is not used by the network layer header, and then it sends this datagram across through some physical link, and for that link you'll need another link layer header. That is received by the destination, and each layer in the destination will then strip off the particular headers and recover the message which was destined for the application. So this whole process is called encapsulation. The message, as far as the transport layer is concerned, is simply M. As far as the network layer is concerned, the message is not M, but it's M plus the transport layer header. As far as the link layer is concerned, the message then becomes the message plus the transport layer header plus network layer header. So all of these headers encapsulate what's happening at the previous layer and send these pieces of information or the bits across. They don't really care what's the physical meaning of the bits inside. Beyond the header, they don't care. Everything else is a message, and then each layer sort of processes these headers in an identical manner, stripping off the header and passing whatever is left back to an upper layer. And finally, it will reach the application. So the next part of the intro is history, and there's nothing really to explain about the history. You can read the book or you can look at the slides of how the internet developed. The history sort of we'll encounter history in different parts of the course when we encounter different layers and how techniques or technologies in the different layers developed. So now we'll start off with the application layer. So these again are slides from the book, made them available on the course website. So we'll the goals of chapter 2 and this part of the course is to understand the application layer and we'll see what we need to develop distributed network applications. What are the services that are needed by distributed network applications? What are the services they offer? What kind of transport layer models they need? What is the paradigm of programming distributed network applications? And then we'll look at some protocols. We'll look at examples of distributed network applications and we'll look at some popular protocols of what kind of specs are needed in these protocols, how these specs are implemented, and then the actual details of implementation using sockets. So before we start on details of application layer protocols, I want to talk about something that is critical for almost every layer of a network. The book really doesn't focus too much on that, but that thing you have to encounter and you have to design if you're trying to create any sort of either network or a network application. And what is that? Well, those are three things that go together: directory, discovery, and naming. So these three things are critical for any networked applications to exist or to function, and for any network to exist and function. So what is directory, discovery, and naming? Well, naming is the protocol or the identification system used by nodes on the network. So again, what we saw, what does a network achieve? It achieves it lets you share information between distributed nodes. So if this node 1 wants to share information with node 2, any network or at any layer, node 1 has to be able to uniquely identify node 2. That is the naming structure. And associated with that naming is the directory structure. So a directory will keep a list of name to node translations. And discovery again is related of how do you discover different nodes which are present on your network, and how do you introduce yourself to the network. So discovery happens in two directions. One is you have to discover other nodes on the network, and second is how you get introduced to the network. Now this directory discovery and naming happens at different layers, and it happens either in a structured manner or an unstructured manner. So what are the examples of naming? On a network. Sorry? A URL. So a URL is, what is the URL identifying?
Location could be a system or a group of systems. These are my URL.
So URL so URL is Uniform Resource Locator. So it's a naming scheme for identifying resources. So it could be a web page, an FTP site, or anything like that. So URL is an example of naming. Any other example of naming on a network? Yeah. Cookies.
Yeah, or it identifies the user to the network.
So it identifies the user, not to the network. So URL is sort of the naming system used on the web for objects, roughly. Cookies more examples? Yeah.
MAC address?
So MAC address is the naming for your Ethernet adapter. MAC address. It's naming at the link layer. Yeah. IP addresses. That's naming at network layer.
Port numbers.
Port numbers. What do port numbers name?
Naming the transport.
Port numbers by themselves won't suffice. So port numbers in some sense name different kind of services that are offered at I'll get to port numbers in detail when we look at sockets. But port numbers, yeah, port numbers combined with IP addresses is a naming convention. Other naming conventions at the application layer. Can you think of anything? Sorry? Email address. Email address, yeah.
Protocoling at the application layer if you're in a web browser, you can do HTTP or FTP or what those protocol names identify the.
That sort of encapsulated by this URL. Another naming system is all of us use instant messaging. So our handle or our screen name is a name on the IM network. So IM network these nodes represent screen names. And you want to talk to different screen names. So you need a directory service to identify what all screen names are there, or to translate these screen names onto a layer below so that this conversation can happen. You need a discovery naming scheme. Okay, depending on the IAM system, they have their own naming scheme. It's any combination of alphanumeric strings. Discovery is very important for a transient network like an IAM network. Why is an IAM network a transient network? Because you log in, you log out. You're not there all the time. So each node has to attach itself to the network, so it has to be discovered by the network, and then it has to discover who else is on the network. So on a very slow time scale, something like that happens when you connect your workstation to the network. But the concept and the principle is the same. You need a naming structure, you need a discovery structure, and you need a directory structure. And all of these principles are repeated at different time scales in these different naming conventions or in the different layers. So when you write a distributed application like an instant messaging application, what are the nodes? Who is talking to? Information sharing happens between what? In the same domain?
Such as AOL versus.
Well, assume that all of these nodes are in the same domain, some same instant messaging domain. Finally, who is sharing this information? That helps resolve one confusion, and that's where also ports and sockets come in. So when screen name, I don't know, ABC is talking to screen name DEF, the conversation is happening between what? Yeah. Two processes. So two applications are talking to each other. So at the very basic level, this conversation is between applications So on your desktop, besides this IM client, you have probably a web browser running, maybe a login session running. All of those are different applications which are talking to other applications, maybe on the same network, maybe on a different network. So to be able to talk to a specific application, you need a way to locate and identify uniquely that application running on the other node. Simply knowing the IP address is not enough. So if we had used only the, let's say, downloading a web page as an example, we automatically think that all you need to get to a web server is the IP address of the web server or the domain name of the web server. So www.cnn.com is enough for our browser to contact the web server and initiate this conversation. Implicit in that is the fact that the browser knows that the web server is supposed to run on the server machine at a particular port. And that port and socket combination gives us a way to uniquely identify the web server application. And it becomes clearer when you think of an IM client. Simply knowing the IP address of the person that you're trying to is not enough. Your conversation should happen between the client at the other end and the client at your end. So the addressing scheme for applications is not the IP address. The IP address gives you a connectivity to the internet, to the network. But to uniquely identify the other application with which you want to talk, you need something else. You need to be able to identify the process. Any node, any network node might be running several different processes. You want to talk to a specific one. And the way that's done is by using port numbers and sockets. So again, creating a network app, we write programs that run on different end systems, communicate over a network. An application layer does not run on the network core. The network core does not care what applications to a large degree are running on it. It provides some basic services. And those basic services are hidden by the layering architecture beyond the transport layer. So all the application knows about is what transport layer it's using. Everything else is transparent to the application. Application architectures we have seen earlier. We have the client server architecture, we have the peer-to-peer architecture. Then there's a hybrid architecture, which is hybrid of client server and P2P. Client server architecture, again, pure P2P we have also seen. Hybrid of client server and P2P is the Napster model or the instant messaging model. In Napster model, the file transfer happens between peers which are connected to the old Napster network. But the file search itself was centralized. So one portion of the application works in the client server model, where the server will give you the search capabilities, and the actual file exchange follows the peer-to-peer model. Instant messaging, again, chatting occurs between two clients, and that is the peer-to-peer model. But the directory and the discovery naming service, that is offered by a centralized server, where you register your screen name. So what really happens is your screen name is attached to an application, which on the other hand is an IP address port pair. So this naming system finally comes down to an IP address port pair naming system which is identified with the process, and that gets registered with the centralized directory system in instant messaging. So when you move machines, the central directory automatically adjusts this translation of between your screen name and the machine where you're sitting at and the specific process which is running your IM client. Because every time you reboot your machine or restart your IM client, the process is going to change. But the directory system has to keep track of that. So a centralized server keeps the directory, but the chatting happens between peers. So that's the hybrid of the client server and peer-to-peer model. So like I said, there are processes that communicate, and these processes run over the network. We already saw what's the conceptual difference between a client process and a server process, not in terms of the information providing model, but more in terms of initiating communication model. The client process will always initiate communication. The server process will reply to an initiation, or it waits to be contacted. So that will come into play in the way we design applications, in the way we write code. A client process needs to do certain specific tasks. A server process has a complementary set of tasks. And the way the sockets are created and the particular function that are used will explain that process. So we'll stop right here. In the next lecture, we'll look at sockets in detail and how do we do socket programming using C. So all these slides are on the website. You can take a look at the socket programming slides in C slides, and you can also read the book chapter on socket programming in Java.